So for section 7.3, we're going to be talking about the product rule for radical expressions. So what this is this. We're going to be using this rule. Well, how do we know this works? Well, again, if you saw 7.2, we talked a little bit about it, but that was kind of getting ahead of ourselves. So let's take a look at this. Now, recall that we can write this as a root. So we can say this is a to the 1 over n times b to the 1 over n. And then we can extract out, or in a sense, factor out this exponent as an exponent. But then we can now return this to a root. And so if we want to take a shortcut, we can say nth root of a times the nth root of b is the nth root of a times b. So that's our product rule for roots. Now, the thing with this product rule is the roots have to be the same. If they're different, it doesn't work this way. So let's do some examples using this trick, if you will. So let's say we have this. The square root of 7 times square root of 5. Well, in this case, we can combine the roots. They're both square roots. Or the square root of 35. Let's try another one. Now again, they're the same root. So that means because they're the same root, we can combine them. And this will be our answer. All right. So let's say we have something like this. So again, same roots, we can combine them. Getting a little ahead of myself. So x minus 4 times x minus 4 to the 4th . And that's going to be your answer. Now let's take a look. Let's say this one. Now again, they're the same type of root. They're square roots. So we can combine them into one root. And then what's going to happen, 5s will cancel and the 2s will cancel. And so what we're going to be left with after simplifying is the square root of x. And that's going to be your answer. So let's do something like this. So again, same root, we can combine them into one root. So 12 times 3 is 36. We have x to the 2 plus 3. And y to the 3 plus 4. And that's going to be our answer. So what we're going to do, this is something where this comes up a lot. And what we're going to do is we're going to reverse the multiplication rule for when we join roots, we're not going to split them up. So we're going to get something like this. It's the same rule, but we're going to look at it from a different perspective. Where we break things up. And this comes up a lot in mathematics. It's a way of simplifying. So let's do an example. Square root of 50. How we break this up can help. We could break this up into 25 times 2. And ideally, when we do this, we want to break it up into a number times another number where one of these numbers has a square root. 25 has a square root. 2 actually does, but it's an irrational number. It's not what you would call one of our canonical square roots that we can read off of or we can find on the multiplication table. And I'll talk a little bit more about this later. But we can write this as this product. And then the square root of 25, we're thinking positive square root. Again, even, it's an even root. 5 square root 2. So that's going to be our answer. So I want to mention this real quick. What is the square root of 2? So we know the square root of 1 is 1. We know the square root of 4 is 2, because 2 times 2 is 4, and because 1 times 1 is 1. Well, what about the square root of 2? What two numbers, what number that you multiply to itself gives you 2? And it's approximately this. And it goes on forever. It turns out that the square root 2 is what is called, and this is the decimal approximation of it, it's called an irrational number. And an irrational number is a number that you cannot write as a fraction or as a ratio. These digits will go on and on forever without any kind of pattern. Now, just because you have digits that go on and on forever does not mean you're an irrational number. For example, 2/3. 2/3, 2 divided by 3. Well, that's a fraction, 2/3. But if you represent it as a decimal, it's 0.6666666666666 on and on forever. It doesn't stop. So just because you go on forever does not mean you're irrational. In other words, there's no way of representing you as a fraction. 0.66666666666 on and on forever, we can represent that as a fraction. It turns out 2/3 doesn't. This you cannot represent as a fraction. So that's why we call it an irrational number. But if you took this irrational number times itself, it would give you the number 2. So if you put this into your calculator, it might round off to 2, but it technically shouldn't. You should get like something that's close to 2, but not quite there. Something just short of 2. So what do we do with this? When we have a square root that's a irrational number, how do we represent it? Well, let's take a look at some of these square roots. So the square root of 1 is equal to 1 because 1 times 1 is 1. We'll get back to the square root of 2 and the square root of 3. Square root of 4. And so what do we do here with square root 2, square root 3? Well, we can write something for square root 1, it's 1. We can write something for square root 4, it's 2. So what do we do for these two? Well, because they turn out to be irrational numbers, it's a convention in mathematics to do this. If this is just going to give you an irrational number, just leave it as square root 2. Same for this one. This one is also an irrational number. So we'll just leave it as square root 3. Now, when we do this factoring, like square root 50, we try to factor out as many square roots as we can. So for square root A, we'll try to factor out as many square roots as we can. And so you'll see this a lot in mathematics. It's a very common thing. So let me do another one. Let's say, for example, the square root of 28. Well, you could write this as the square root of 4 times 7. Again, a number that has a square root. And so we could do square root 4 times square root 7. Square root of 4 is 2. So you have 2 times square root 7. Square root 7 is another irrational number. So we're just going to leave it. And so we get 2 square root 7. And that would be your answer. And what if you're not sure? Like, let's say we do square root of 32. And I'm not really sure how to break this one down. What we can do is we can break it down to prime factorization. And, well, one thing to keep in mind, every 2 times 2 is a 4. So this is something that we can take the square root of. So that means number we can take the square root of, number we can take the square root of, and then a number that we can't. Again, this will break up using our product rule. Square root of 4 is 2. Two times 2 is 4. So that's one way of doing this. Now, there are other ways of doing this. You could have recognized that this was 2 times 16, and you can take the square root of 16, which gives you 4, and that leaves behind a 2 in the radical. But let's say you didn't know that. Well, this is one way you could break it down using a prime factorization. So let's say we have this. Well, let's break this down and try to see if we can break it down in terms of a number that has a square root. And we can, actually. 3 times 25 is 75. Well, 3 doesn't have it's going to be an irrational square root. Can't say anything about x. And again, we're assuming that x is a positive number here, or 0. So we'll get square root 25, square root 3, square root x. Square root 25 is 5. So we'll get 5, square root 3, square root x. I'll be honest, this is kind of messy. So to make it a little simpler, we're going to merge these two roots because they're the same root. And there we go. Now let's say we do this. Now what do we do here? Well, negative 32, we're dealing with a cube root. So we want to try to get negative 32 in terms of a product of numbers where one of them has a cube root. And there's one that comes to mind. Negative 8 times 4. Because negative 8 is negative 2 times negative 2 times negative 2. So the cube root of negative 8 will be negative 2. Now there's another thing that's going to have a cube root here. Y times y times y. And these right here, 4x squared, 4 doesn't have a cube root, at least not, and well, it does actually, but it's going to be, again, irrational. If you try to compute the cube root of 4, you'll get an irrational number. Now, you can compute the square root of 4, but that's 2. But the cube root of 4, not so much. It's going to be irrational, so that means we're going to leave it. And we have x times x. We really need a third x in there before we could take the cube root, unless we're going to get a rational cube root, which is fine, but we're going to try to keep things in terms of the root. We're not going to turn things into rational exponents. So what we can do, cube root negative 8y cubed times the cube root 4x squared. This will turn out to be irrational. Really want to get an extra x in there, but we don't have one. So cube root of negative 8. Cube root of y. Cube root of negative 8 is negative 2. Oh, got cubed in there. Cube root of y cubed is going to be y. And this is going to stay the same. So for our final answer, we'll get negative 2y cube root 4 x squared. All right. Now, we're going to backtrack a little bit to the extent that we going to assume that x could be negative. So for this next example, let's assume x could be negative. So for that case, I'm going to do this a little differently now. So that means if we have the even root of an even power and the root and the power match, we're breaking out that absolute value. So let's take a look at this. Now again, square root of 36 is 6. We have a square root. So we're going to try to simplify this. Now, we could approach this different ways. We can say that, well, this is 6 squared. The positive square root of 6 squared is positive 6. Or we could just say this is the positive square root of 36, which is 6. Again, with those even roots, you got to be kind of careful of this sort of thing, the positive root and the negative root. Now for this one, the square root, or the root 2 of something being squared. So this means if we assume that this could be negative in here, got to take the absolute value. And that's going to be our answer. Now, if we weren't allowing for the fact that variables could be negative, the absolute values would go away. We have 6 times the quantity x plus 2. But not in this case. Let's see here. this one. So let's break this up. Cube root of the number, cube root of this. So one thing we can kind of take to heart, when we're dealing with an odd root and an odd exponent, same root, same exponent, things just disappear. We don't have to worry about absolute values. So we're going to get cube root of 48 times x minus 2. It just pops right out. Now 48 is kind of tricky. You could break this down different ways, but one way you could break it down is this. 16 times 3. And this, oh, wait, that won't work. This is a cube root. Oh. Well, let's break this down a little bit more. Well, we can still do 16 times 3, x minus 2. But we have a square root for 16. We don't have a cube root that's rational. We only have an irrational cube root for 16. So we can try this. Now we do have a cube root for 8. And what we could do, instead of 2 times 3, we can call this simply 6. Now we don't have a cube root for 6. We don't have a square root for 6. So what we can do is take the cube root of this 8. So sometimes you got to kind of play around with the numbers a little bit, and that's fine. Just make sure you catch it before you take a square root of 16, and you need to be careful of a cube root of 16, which you don't want to do. Cube root of 8 is going to be 2. Now let's take a look. Let's see how they want this answered. So the answer format they give in the book is 2, x minus 2, and then the cube root of 6. It's very common to have the root go last. So that's a format just to be aware of. All right. So let's see here. So what we're going to do next, we're going to go back to this idea where the variables are all positive or 0. We're going to allow this. So let's do some examples with this. So let's say we have the square root of x to the 5th. Well, we can write the square root of x to the 5th as x to the 4th times x. And what we want to think about is this. We can take the square root of x to the 4th, and here's why. X squared times x squared is x to the 2 plus 2, or x to the 4th. Something times itself gives you x to the 4th. So the square root of x to the 4th is x squared. So we'll get x squared times square root of x, or x squared, and again with the radical coming last. All right. So let's say we have something like this. Now, if we want, we could break this up into the number times the variable. We could do that. So square root of 40 times square root of x cubed. Now, square root of 40, what we're doing with square root, we can do it as, say, 4 times 10. Because 4 does have a square root that's not going to be irrational. Unfortunately, the square root of 10 will be irrational. Now, this one, we can break up as x squared times x. And the reason is the square root of x squared is x. X times x is x squared. Just like 2 times 2 is 4. So we know the square root of 4. We're going to know the square root of x squared. That's going to be 2. Going to be x. And when we combine these, again, we'll put the roots last. We'll get the 2x, square root 10, square root x. Now, square root 10 and square root x, if we merge these, because they do have the same root, and that just cleans things up. And that's going to give us our answer. So let's take a look at another one here. Ooh. So what about this one? Well, we can break it up number and variable. So what we can do here, 64, is there a 5th root for 64? Well, let's see here. 2 times 2 times 2 times 2 is 16, times 2 is 32. So if you take 5 2s and you multiply those together, you'll get 32. Throw in a 6th 2, you'll get 64. So we could break it like this. 32 times 2. And the reason being is 32 has a 5th root. It's 2. What about this? Well, this we can break down as x to the 5th times x squared. X to the 5th has a 5th root. It's 5 x's multiplied together to give you x to the 5th. And so the 5th root of x to the 5th will be x. Now this one's a little tricky, but you can argue correctly that y to the 15th has a fifth root. So here's why. You take 5y to the 3's, multiply them together, you'll get y to the 3 plus 3 plus 3 plus 3 plus 3, or y to the 15th. So that means the fifth root of y to the 15, 5 of those, is going to be y cubed. So we'll get the fifth root of 32 times the fifth root of 2 times the fifth root x to the fifth times the fifth root of x squared times the fifth root of y to the 15 times the fifth root of y. So now we do our computations. Fifth root of 32 is 2. Fifth root of x to the fifth is x. Fifth root of y to the 15 is going to be y to the third. And what we can do is we can merge things that are not in roots. So we have 2xy cubed. Then we have our roots. Fifth root 2, fifth root x squared, fifth root y. And we can combine these into the same root because they are the same root. So we'll get 2xy cubed times the fifth root of 2x squared y. And that would be your answer. Now let's see. Now, I do want to show you kind of a trick. Let's talk about the fifth root of 16, y to the 16. I'll admit, that was kind of a clever thing that I did, breaking up into y cubes all multiplied together. So this is what you can do. Remember that a root is a rational exponent with a 1 as a numerator. Distribute and multiply, you'll get y to the 16 over 5. Now, there's something you can do here. Let's divide 5 into 16. Because this is division. Well, it goes in at most 3 times. 3 times 5 is 15. Subtract, you get a remaining 1. So that means the answer is 3 plus 1 over 1/5. So 16 over 5 is equal to that, if you do the long division. So this means this is equal to y to the 3 plus 1/5 when all is said and done. Or we can call this y to the 3 times y to the 1/5. Turn this into a root. Y cubed, fifth root of y. So if you're not sure how to break this up, you can turn this into a rational exponent, distribute it to this, so you get 16 over 5. Do the long division, 16 divided by 5. That's what 16 over 5 means, and you'll get this. 5 is in the 16 at most 3 times with a remainder of 1. And the way we express a remainder is we always add it and put the divisor underneath the remainder. And then this means multiplication of the same bases. And then turn this into a root and you're done. So now we're going to go the opposite direction. And this might seem a little redundant, but once we do these multiplications, we're going to have to reduce things or simplify them. So same root, 12 times 2, 24. But we can break this up. A number with the square root, number 6. Square root of 4 is 2. Square root of 6. And that's going to be your answer. Now again, they have the same root, so we can combine these. So we get 50, x times x is x squared, y times y squared is y cubed. Can we simplify this down? Well, again, we could break it into the number, the variable. And again, we're assuming all the variables are 0 or greater. Again, no negative values for variables, so we're not going to worry about having to take absolute values. Now, this one, can we break it into a number with the square root times another number? And we can. Well, the square root of x squared will just be x. X times x gives you x squared, so square root of x squared will be x. We'll keep that there for now, though. And this one, we can make it into y squared times y. So this will give us so again, we can combine the non-roots, 5xy, and then we have the roots trailing at the end, and we can combine the roots. Same roots will become one root. And that's going to be your answer. Let's do one more. Let's say we have this. say you have something like this. Well, same roots, we combine into one root. So we can combine them if we want to. We might want to, you might be thinking how we could maybe break this up. Now, what we could do, let's think about this 3 and the 7. This, oh, I'm sorry, 8. Ooh, careful. So what would be the cube root of something to the 8th power? Well, again, we can get kind of creative here. So we could say this. So if you take x minus 6 squared, and you take 4 of these and multiply them together, you'll get x minus 6 to the 8th. So there's 4. We're looking for a cube root. Well, what we can do is this. These right here will multiply to give us x minus 6 to the 6th. And clearly, because x minus 6 to the 6th has 1, 2, 3 of these, well, then the cube root of this is going to be this. And then this extra one is just going to be left behind. So we can rewrite it like so. We can do that. So we break it up. And this we know the cube root of. This one we really can't do anything with it. If we had an extra x to the x minus 6, we had x minus 6 cubed, well then we could do this, but we don't. So we're just going to leave it this way. And that's going to be our answer. So that's going to be it for section 7.3. If you have any questions, let me know. We're going to look at adding and subtracting in the next section, 7.4, and then we're going to look at the quotient rule. And that'll take us to our, if not, yes, it'll take us to our chapter midpoint. And then we'll do some more things with these radical expressions. So other than that, have a great day.